Okay, so Saint-Venant's principle is definitely one of the most important modeling principles when it comes to finite element structure modeling. It's a very short section in the prescribed textbook, but it's definitely an extremely important concept to understand, as it allows you to make decisions on when do you model something with detail, or when do you approximate something when it comes to modeling. So what we're going to look at is specifically now a couple of examples of modeling, for instance, a loading onto a structure. And the reality is, when we want to model, let's say, a uniform beam, we apply load, we want to pull it. If we're interested in the answer close by to where we model the load, then it's important to model that loading with as much detail as we can, so that the answer is representative of the actual answer, close by to where the loading is applied. If, however, we're interested in the loading far away from where the loading is being applied, then we can have any essentially statically equivalent load applied to being replaced by the loading that it's supposed to be applied for you. So, for instance, if we have a uniform, let's see if we've got some pictures here. If we've got a uniformly distributed load applied to a structure, like in this case here, so this is the structure, it's a millimeter thick, and this is the loading that we're applying, is this load T. If I'm interested in the answer far away from that, I can replace this distributed load, the way it's modeled here, with a pull, for instance, with a load where I'm just pulling on this. And the answer far away here would be representative of the actual answer. If, however, I'm interested in knowing what the answer is, let's say here, close to where I'm applying the load, then I should be modeling this as a properly uniformly distributed load. That is important to understand. Then I'll have to model this as a properly uniformly distributed loading. Okay. Because if I were to approximate this as something else, like for instance, let's say a point load, I'll get large variations between the answer of this and the point load, which will influence my answer close to where the load is applied. And so Saint-Venant's principle tells you, if you are interested in the answer far away from where you're making certain modeling decisions, you can simplify those modeling decisions as long as they're statically equivalent. If, however, you're interested in the answer close by to where you're making modeling decisions, then you have to make those ones as accurately as possible. You need to model them as accurately as possible. Really powerful message that Saint-Venant's principle is sending. It really allows you to distinguish between where should you put your modeling effort and where can you make modeling simplifications. It's really the vehicle that allows you to make those decisions. Okay, so essentially Saint-Venant's principle is named after Allemand Jean-Claude Bar de Savant, a French elasticity theorist, and let's read formally what it says in terms of the sort of the formal statement from him. It essentially says the difference between the effects of two different but statically equivalent loads becomes very small at sufficiently large distances from the load. Okay, so that's essentially what that says. Okay, that I put in there. It's just from load. Okay, so that's really what that message is all about. So what we're going to do is we're going to look at essentially modeling a structure. We have a uniformly distributed load at the right hand side. It's equal to uniformly distributed loading that we have here, and we want to understand what is the stress in the structure. Okay. And if we do a sort of quick hand calc of this, if it's a millimeter thick, 4 millimeter high, it's a 4 millimeter surface area, cross-sectional surface area. We're applying a total force of 600 newtons. So 600 divided by 4 is 150 MPa. That's sort of the stress that I want to see. Okay, And if I look far away from this, on the opposite side here, I want to see essentially about 550 MPa. If I look close by, if I'm interested in the answer close by, then I need to make sure I model this properly so that I do see indeed essentially a close to 150 MPa. So we know what kind of answer we're looking for, just in the ballpark. Okay, from my hand calc. So I'm going to show you three FEM models. So we're going to go through three models. The first model is we're going to model exactly this with rollers and a clamp here, but we're going to apply a single load of 600 newtons at that mid-side node. It must be statically equivalent. So what does it mean? What is the sum of forces, the sum of moments, etc.? All of those things must be the same. So if I tell you, if I apply a district like this, sum of moments tells me essentially that it's 0. If I take sum of moments at any point, I'm not going to have any moments that will generate. Okay, you can easily see that by saying, let's just say sum of moments at this point, these moments and these moments on both sides cancel out, sum of force in the x direction and sum of the force in the y direction. Must be all statically equivalent. Okay, so that's a statically equivalent load. There's no additional reduced moment. Sum of force in the x is still so the forces that's in the x applied in the x direction is still 600 and in the y direction is still 0. Okay, that's one model that we can have. A second model we can have is doing this, where we're splitting the loads equally across the nodes. So this is something that's not related to consistent node loads. As a matter of fact, you'll be very pleased to see that if you wanted to apply consistent node loads, the split that we use here, the split that we get for if it's a uniform discrete load, is the same split as what we saw for the body forces in the 1D case. So essentially 1/6 of the loading would go here, 2/3 here, 1/6 here. It's beautiful. And that's really what we see here. So if there's 300 newtons on this element, and it's 300 newtons being applied on this element, so 300, it's all constant and uniform, then essentially 1/6 of 300 is 50, 2/3 of 300 is 200, and then these add from these two elements. There's a 50 from this element and a 50 from this element and a 50 contribution from this element towards this node. That's why you have 100, 2/3, and then 1/6. So the consistent node loading essentially split ratio is the same. And it's because when we evaluate a quadratic Q8 element on an edge, what we recover essentially, and you can go see that, check that, double check that for yourself. As soon as we substitute in a value, we essentially recover sort of a quadratic Y elements behavior on that edge. Okay, so that's really important just to understand that now we also have covered, in this example here, we're covering essentially also extension from 1D to 2D. What happens to the consistent node loading? So if you take the shape functions of a Q8 element, we evaluate for, you can imagine in the local coordinate system, we would evaluate it at psi equals to 1 on that edge. So this would be a function of eta. And if you integrate along eta, along this edge, we recover essentially the split that is required. Okay, for how the distributed light should split across there. So those are going to be the three models that we're going to be looking at. So let's now we've set the scene. Let me see what the time is. So I'm going to stop this video. So next one we're going to look at problem 1, and then problem 2, and then